Okay, so let's look at another example. And so now I'm not necessarily going to go through the math of all these examples, but I just want to show how we can apply this method of images where if you're presented with a charge and say a grounded plane of some sort, we can think about where I should put image charges to have an equivalent or easier problem to solve. So let's look at two more examples that we'll sort of just talk through the geometry rather. So let's look at this example where I have a charge that's in sort of the first quadrant of an XY plane. So I have a plus charge right here. And let's say that it's a distance A from the x-axis. So in the y direction, it's gone A off the x-axis. And in the x direction, it's sort of B down the line there, right? So we have this charge, and this in this setup here, we're going to have another sort of grounded plane, and that plane is going to be sort of somewhere along here. And instead of it just being a single plane, it's going to be kind of a corner sort of shape, where the plane goes off to infinity in the x direction, the y direction, but we have this kind of corner where the Q is sort of hanging out inside there. And so when we had this plane before, remember that really all we did was we reflected the charge from one side of the plane to the other side of the plane, and then we got rid of it. But we want to be careful here because we sort of have two different planes to worry about, the one on the vertical and the one on the horizontal. And so we have to we have to mirror along both planes. And so we'll do it one at a time. Let's just mirror it along the vertical plane. So I'm not going to worry about the grounded piece that's along the x direction. Remember that both of these are grounded, so I want v to be equal to 0 there, right? And so I'm going to do this in two steps. The first step is going to be to flip or mirror it along the vertical plane, right? And when we do that, we're going to have another sort of setup here, another set of axes. But here's my x-axis, here's my y-axis, and I still have my regular charge, and it's still a distance a. But now, since I've flipped it, I have another charge that's over here. And so if this was a distance b from the y-axis, since it's a plane, not a sphere or anything like that, we have another charge that's a distance b. But if this one was plus q, then this one has to be minus q, right? And this one is still a distance a. However, when we flipped that, we can now get rid of the plane that was vertical, but we also have to keep the plane that was originally here. So the horizontal one is still there. And even more so than that, we still have to keep the plane after we flip it. So we're flipping the charge, but we're also flipping the plane. So this plane now continues all the way over to this side. And so the idea is we've dealt with the vertical thing, and so now this problem and this problem are equivalent problems, right? So if I can solve this problem, that solution will be the exact same as the one up here, right? However, this problem is still also not so easy to deal with because I still have this infinite grounded plane. And so I'm going to take it one step further and do the same thing again. And now we're going to flip along the horizontal plane. Right? And so now I have, again, another set of axes. And oops. But now I'm going to have to flip in the other direction. So I still have my charge plus Q, still a distance A here, and a distance B here. And since I flipped it from the previous problem, I still have this charge. This is an image charge, and it's still at the same place it was before. So it's B to the left of the y-axis and A above the x-axis, right? But now I've flipped it along this horizontal plane, and so just like the problem from before, we're going to flip these charges. So now I'm going to have a charge down on the bottom, and that will be negative Q, and that's going to be a distance A from the x-axis, and still a distance B. And then I'm going to have another charge down here that's the opposite of this guy, so that's going to be plus Q, and that will still also be A and B right here, right? And so now this problem and this problem are equivalent. And so the idea is that since all of these are equivalent, they all have the sort of the same boundary conditions. Now we have this 4-point charge problem. We know that it will have the same solution as the single charge with the corner plane. All right, so we've sort of come up with, in 2 steps here, we've come up with a problem that has just 4-point charges, and again, point charges are always easier to deal with than having to mess around with this boundary condition for these planes. I just want to kind of re-emphasize here this important point that there can be whenever we're doing this kind of flipping procedure, there can be no image charges in the original area. Meaning I have 3 image charges, right? This is an image charge, this is an image charge, this is an image charge, this is a real charge. I can never have any image charges up here in this first quadrant. So for our example, if I were to have done all this flipping and then somehow I did some sort of flip where I ended up needing an image charge up here in the first quadrant, that means I can't use method of images and it just won't work. So there can never be any image charges in the original area that we started with. And now in this case, we don't have that, so that's okay. We can still use this, but we have to also keep in mind that our solution is also only valid in the original region. All right, again, for this problem, the first quadrant. So even though with these point charges, I could certainly find the potential due to all these point charges in the second quadrant, but that is not the original region that we were dealing with over here. And so whatever potential I get on the first quadrant, that's fine, but that doesn't mean that I know what the potential is sort of on the other side of all these planes. Okay.